Hello everyone. Uh, Welcome to this introduction video. In this video, I'm going to give a short introduction to the new theory of everything in town, which I call dynamic general relativity. Uh, this is the book which I'm talking about. This is the book written by me. I'm Rohit. Yes, I'm a medical doctor, but I don't have any PhD or anything. So, name of the book is Decoding Gravity, Time and Causality. In this, I describe this new theory of everything, which I call dynamic general relativity. It is basically general relativity redefined at quantum level. So this book is going to come in another 2 to 3 weeks time, hopefully the first or second week of January worldwide. So I'll be just giving an introduction, very short, brief introduction. So this book is basically describing this DGR, which is actually a theory of quantum gravity and a potential theory of everything. So there are going to be some who are hearing this video who may not be very good at physics. So I'm going to go slow and I'm going to keep explaining things. So those who are experts in physics and who know all these things, they can just jump to about 4 or 5 minutes into this video. And so what is this quantum? These are basically very heavy terms. So quantum is basically very small. Quantum, in real sense, it doesn't mean very small. It means packet, but a small packet of energy. That is the place where quantum started. And now, in contemporary physics, quantum means very small. So a quantum particle is a very small particle. Electrons and protons and all those things are quantum particles. So they are in the range of 10 to the power minus 18, 10 to the power minus 15 meters. 10 to the power minus 15 is proton. 10 to the power, that is a femtometer. 10 to the power minus 18 is an electron. So these are extremely small distances, and these are basically quantum particles. So quantum is basically very small. So quantum gravity is actually the events which are happening at an extremely small level, at quantum level. In our theory, they are not happening at these levels. Actually, they are happening at Planck scales. Planck scales are even smaller. I'll come to that. But so these are events which are happening. So it's basically a phenomenological description. So there is not much mathematics in it. It's a phenomenological description of a new theory of quantum gravity, which describes events which are happening at Planck scales. And theory of everything for lay people, theory of everything would probably mean a theory which describes everything. But from physics point of view, it is a bit different. From physics point of view, a theory of everything is it should not necessarily describe how consciousness works or how life emerges or how self-organizing systems form. So these things are out of that theory of everything. So although it is called as a theory of everything, there are many technical definitions of a theory of everything. So I'll explain to it a bit, but not to a great detail. So there are basically two theories. One is a theory of the very small and a theory of the very large. So quantum mechanics is the theory of the extremely small, that is quantum particles. So these are basically rules which apply only to small quantum particles. So this is not a single theory. It's a set of theories. So this is a standard model of particle physics and quantum field theory. So these are basically the accepted things in this quantum realm. These are basically extremely well tested theories. So we have little doubt that quantum mechanics is wrong. So we know that it's correct. It gives extremely accurate results. And also the theory of large is general relativity. So this is also extremely well tested, and a lot of experimental verifications of general relativity have come. So there's little doubt that general relativity is wrong. But we also know that both quantum mechanics and general relativity cannot be right because they are incompatible theories. So quantum mechanics happens in its own realm, where gravity is very, very weak. So general relativity and all predictions of it can be neglected. And general relativity happens at realms which are actually in which quantum effects are very negligible. So though they can be neglected. So at present, they are basically two completely separate theories, and they are incompatible theories. And ideally, a theory of everything should basically combine them or reconcile them. So this quantum mechanics is basically dealing with the three fundamental forces, and general relativity is the theory of gravity. Actually, we know that quantum mechanics is a bit tricky because we know that there are things in quantum mechanics which really don't make much sense. Like there is something called as entanglement. There's something called as superposition. That is, an electron can be in one position at three different positions or multiple positions at the same time. So these are some counterintuitive things in quantum mechanics, and even general relativity has its own problems. Uh, Although we say that it is a theory of the large, it works good till the solar system, but once it goes beyond that, at distances of more than a light year, that is hundreds of thousands of light years apart, the gravity which is predicted by general relativity is actually it falls significantly short of what is observed. So we have to postulate something called as dark matter. We'll come to that. But basically there are some problems with general relativity, and also there is a problem of time. That is, some aspects of general relativity, some interpretations steer towards block time. So all in all, these are extremely well tested theories, but these two theories are incompatible. So we basically have to reconcile these two. So why they are incompatible is because there are two problems: background problem and problem of time. So background problem is what, that in general relativity, background is an active player. So it can basically, it's space time. So it can expand and contract, and it can carry the forces. But in quantum mechanics, the background is a steady player. So it is not actively involved in transmission of forces. So transmission of forces is done by something called as force carrying particles or bosons. So in quantum mechanics, background it's a steady background, so it cannot expand or contract. This is also true for time. So in general relativity, time is not absolute; that it's a relative. And it is married to space in general relativity. But in quantum mechanics, time is a background entity. It is basically moving forwards at same rate for every point. It is the same. So this is basically the difference between the two, and that's why quantum mechanics and general relativity are completely different. So there are four fundamental forces of nature which we know: electromagnetic, weak force, strong force, and gravity. So we know that this electromagnetic force is the one which binds the protons and electrons together, and they form atoms because of that, and molecules, and because of this force we are basically we owe our existence to this force. But not only that, strong force which keeps the nucleons together is the which keeps the quarks together inside the nucleus, and which keeps the protons and neutrons together in the nucleus. So it enables the formation of of atoms and higher molecules and all. So these are extremely important forces. So now weak force is basically a force which occurs commonly in the sun, but it is basically a heavier element getting transformed into a lighter element. So it's a anomalous type of force. Anyhow, so these three forces are quantum forces. So they are basically acting at very short distances. Although electromagnetic force, the range is infinite, like gravity, but these are short range forces basically. And gravity is the long range force. So the upper three are basically the theory. The quantum field theory is the thing which governs these three forces. And gravity is basically an odd man out, because in standard model there is no gravity, so it cannot be incorporated in standard model. That's one of the problems. So there is this guy called Isaac Newton. So this Newton, what he did was he told us that terrestrial gravity and celestial gravity are manifestations of one of the same force. That is a falling apple and Earth revolving around the sun. These are because of the same force. Similarly, Maxwell did the same thing to electrical and magnetic forces. So he combined them together to form electromagnetic. And electromagnetic force and weak nuclear force are combined together by Weinberg and Salam to achieve electro-weak unification. So you don't need to understand all these, but basically, so this unification era, there's a hint that grand unified theories are theories which basically unify electromagnetic, weak and strong nuclear force. And theory of everything unifies all the forces, all these three fundamental forces, with the force of gravity. So it's a sheer hope that theory of everything, if it does exist, should unify gravity with all these forces. So it should tell us that there is a single fundamental force which basically manifests as four different forces. So what should a theory of everything do? A theory of everything should unify all the forces, ideally, um, if the physicists are right, and nature is simpler. Simplicity is one of the characteristics of nature, which is what is thought of. Then unification of all forces it should do, and it should make quantum mechanics and general relativity compatible. So this is just one thing. These are just a few things which there are many other things which a theory of everything ideally should do. Ideally, a theory of everything should answer. There are a lot of enigmas in physics currently. One of the enigmas is dark matter and dark energy and cosmological crisis. So this, as I said in the previous this thing, that the general relativity basically is a good theory until solar system. So after a solar system, the gravity provided by it falls short. So if you start from the sun and go away, and you measure the rotation velocities of planets, then the velocity keeps reducing. It keeps reducing. So scientific logic says that the same thing should apply to the gravity of the galaxies, but it doesn't. So contrary to logic, what happens is when you go from the central part of the galaxy towards the periphery, the rotation velocity of the stars should ideally decrease as per Newtonian gravity or Einsteinian gravity. But what happens is that it keeps increasing, and then peripheral stars rotate with rather revolve with a constant velocity. So this is called as a constant velocity rotation velocity curve. So this is an enigma. So for correcting that, we have to postulate something called as dark matter. Now this nobody knows. It's a dark dark source of gravity. Nobody knows what it is. Either you have to postulate that exists some matter called as dark matter, or then you have to modify gravity. So this theory of everything should do away with dark matter ideally, or then it should tell how the dark matter is, what is it, and how to basically solve the how to detect dark matter. And also cosmological crisis is another very interesting enigma. That is, um, the universe is expanding, we know that, but we also, recent observations have suggested that the universe is not only expanding, but it's expanding um, faster and faster. So its expansion is accelerating. So um, scientific logic says that if you think about an energy called as dark energy, which is causing the expansion. So as the universe gets expanded, the volume increases. So the amount of energy should reduce. But what is happening is that if the energy is reducing, that means the expansion should slow down and gravity should take over. But that's not what is happening. What is happening is that the universe is behaving anomalously again. So it keeps expanding, and its expansion seems to be increasing further. So this is called as cosmological crisis. So there's something called as Hubble's constant. Um, so Hubble's constant shows that the so accelerated expansion of the universe. Nobody knows how. So it should basically, the theory of everything should solve this problem. There are many other problems actually. I'm not going into details of all these problems, but is what is a black hole? What is the singularity at the center of the black hole, where our theories they fall apart? The dynamic general relativity, rather general relativity, the equations just don't make any sense. Our maths just falls apart. So there's another problem called as matter-antimatter asymmetry. So something called as what happened at the start of the universe, whether there was a big bang, whether there was inflation. There's another problem called as information loss in a black hole, and there are some CPT violations. So these are all problems which are grave, and a physicist should ideally, an ideal theory of everything should be able to solve all these problems. What a theory of everything should do, according to me. To me, these are very important, but there are some other important things which I would want a theory of everything to solve, which I don't know whether physicists would agree. But yes, what is light? We know that light is made up of particles, which are called as photons. Einstein called them photons. We also know that the light is made up of waves. So we don't know exactly how light is, what light is, like whether light is made of particles or it's made of waves. How exactly is this wave particle duality? We don't know what exactly is waving, what exactly is the wave front. So um, similarly, what is time? We don't know. As I said, general relativity is an accepted theory. Uh, it tells us that time doesn't exist. It's an illusion. That is, time. There is no past, present, and future. So there is no distinction between the two. So there is something called as a block time, which is very counterintuitive. So ideally, I feel that time is something which we are not understanding well, and the theory of everything should ideally make it clearer what time is, what is energy. So we know that energy, a bullet has kinetic energy, but where exactly is that kinetic energy? We don't know. TNT has chemical potential energy, which when you burn it and it blasts, it has a huge amount of energy trapped in it. But in which format, we don't know. So chemical potential energy, we don't know where it is. Potential energy, we don't know where it is. Kinetic energy, where it is. What is inertia? We don't know. So these are all questions which have been basically brushed under the carpet, saying that yes, this inertia is basically a law of nature. So this happens because nature is like that. It's a law of nature. But why it happens like that, we don't know. So ideally, this theory of everything should explain all these things in much more detail, and it should explain all these things. There are other abstract entities in physics, like fields are there now, momentum is there, kinetic energy, potential energy, we just mentioned. Superposition and entanglement, these are things in quantum mechanics which are counterintuitive, and we need some explanation what exactly is this superposition, entanglement, wave particle duality, and what is the spin of a particle, what are virtual particles, what are fermions, bosons, Higgs boson. So these are basically pretty tricky questions which we have accepted um, as it is on face value, without further digging into it what they are. So ideally a theory of everything should be able to explain all these things. So the question comes, that there are thousands of physicists working all throughout the world to solve the problem of quantum gravity and theory of everything. So do we really need another theory? Why do we need DGR? So that's right, actually. There are so many theories of quantum gravity. This is not an exhaustive list. So the first two theories, that is loop quantum gravity and string theory, are the most important theories, and most of the physics manpower is involved in these two theories. But the other theories are also very, very interesting. I have to say that I don't know in detail about the mathematics of any of these theories, but uh, uh, as far as loop quantum gravity is concerned, it is the foundational theory of DGR. And when DGR started, I started with loop quantum gravity, and um, fortunately, as the theory ended, I found string theory emerging out from DGR. So basically, DGR can be called as a bridge theory between loop quantum gravity and string theory. And in reality, this causal dynamical triangulation is another theory which pops out of DGR at a proper intervals, at proper levels. And DGR is actually an emergent theory, emergent gravity theory. So like entropic gravity is also, although I don't know detail, but just superficially, DGR is like an entropic gravity theory. So what I believe is that all these theories are important, and these theories look at a single problem with different perspectives. So all of them have something right and something wrong, and we have to um, basically differentiate between what is right and what is wrong. So um, as far as DGR is concerned, yeah, so the DGR, a lot of other theories pop in out of it, like Newtonian gravity and general relativity also pop out of it literally, and even quantum field theory. You can or the standard model. It can make sense with DGR. So there are some candidate theories for theory of everything also, but there are not many actually, and it is just a string theory which is the most important theory of everything, candidate theory. There are some other things like geometric unity and Wolfram's project, which basically tell us to think out of the box, but I am really not aware of these theories, what they think and all. But I think that every attempt to look at the reality at its um, closest or at its most fundamental level, I think it should be appreciated, and it should it has something good and something bad. So you have to differentiate between what is right about the theory and what is wrong about the theory. Um, so anyhow, I think that um, it is definitely needed, DGR. Anyhow, the current theories which are there, especially loop quantum gravity and string theory, there are some drawbacks or difficulties or problems with these theories. They are basically lost in the theoretical realm. So it is so much into theory and it's so much into mathematics that the mathematics has become so complicated that a layman cannot understand them at all. And they are so much in theoretical realm that they have no testable experimental predictions, so they cannot be tested. And all their predictions are either they don't make any predictions like string theory, or they might make predictions, but the predictions are beyond the experimental energy ranges. So you cannot possibly test them. These last two are also extremely important. There are too many free parameters. So in string theory, 10 to the power 500 different Calabi-Yau manifolds are there. So you just cannot expect any prediction from these kind of theories. So there are too many free parameters or constants. So if you have any difference in experimental and theoretical predictions, then you just add some parameter, some constant, some variable, and that's how it's a not a sign of a good theory. So some of the theories are non-falsifiable theories, like string theory. Whenever there is some problem which comes, some internal tinkering is done, and then again it is they'll not completely change the direction of thinking, but they will do some internal tinkering and then make the things theory viable again. So ideally, what is the characteristic? What are the characteristics which a ideal theory of everything should have? It should basically have minimum assumptions. So the total number of assumptions should be hardly a handful. It should, the quantum field theory which is there has to assume 37 different kinds of fields, one field for one particle. So it's like 37 different fields just we have to assume, plus 20, more than 20 constants you have to add up into the theory, because the theory cannot derive those constants, and you have to put those measure those constants experimentally and add to the theory. So basically theory ideally should have minimum number of assumptions. An ideal theory of everything should be a bridging theory, so it should be capable of deriving other accepted theories. So other theories should start popping out of the theory at appropriate levels. Ideally an ideal theory of everything should be adequately specific, so it should not be infinitely changeable. So if you have a theory like quantum electrodynamics, which you can keep adding as many number of variables as needed, as many number of Feynman diagrams you want, you can keep adding. So that's a sign of not a good theory. And Feynman actually accepted that this is true, that it is a hocus pocus, and so this is not an ideal theory. So an ideal theory should be not be non-falsifiable. Means what? Should be falsifiable. So if you have your theory is good, then it should make some predictions, and if the predictions prove to be wrong, then the theory is falsified. So you just stop that thinking in that direction and go into some another direction. Ideally, that should be the theory, but that most of the theories which presently are not non-falsifiable. So they are too general. They are not specific enough. So it should be able to ideally capable of giving experimentally testable predictions, and it should have minimum number of constants. So ideal theory should actually have zero constants. So all the constants of nature should pop out of the theory without much problem. So if you have to tinker too much and you have to put a lot of constants in it, then it's not a really good theory. So you need another theory probably. So total number of theories of everything that fulfill all these criteria is none actually. So it is true that even DJR doesn't fulfill all those criteria, but DJR comes very close. But DJR is very it's actually is in its infancy, and it's just a theory at present. So it has to basically go through a lot of rigorous, physicists have to go through it, and it has to go the test of mathematics and also experimentation. And so Dichar is also not an ideal theory of everything, but Dichar comes very close. Actually, it comes very close, and as I'm very hopeful that as time will go through, and more and more things will become clearer, Dichar will come pretty close to an ideal theory of everything. So if there are so many theories, it's like 1 century has passed since general relativity came, and almost 60 years have passed since quantum mechanics was completely finalized. After that, hardly anything has changed in fundamentals of physics. So what exactly, where are we going wrong? So actually, there are many mistakes, but what I feel is one of the biggest mistakes where we are making is time. We are not able to understand time. I believe that time is the key where we have to understand. We have to understand time much better. Anyhow, now I will. It's just an introduction of theories of everything. Now I'll come to the topic which you are here for, DGR. So dynamic general relativity and general relativity. What exactly is the difference? To tell you the truth, there's not much difference at human scales. Human scales, dynamic general relativity exactly looks like general relativity. General relativity is actually, it literally pops out of BGR. But they are two completely different theories, completely different. And especially at the quantum level, they are completely different. So what exactly is the difference? For that, you have to go into a bit of a history. Special relativity came in 1905, and general relativity came at least actually came much earlier than this, 1915. But he gave the field equations in 1915, and it was basically the experimental confirmation came from Sir Eddington in I think 1919 or something, and that made him famous. That made Einstein famous. So um, when he was formulating general relativity, special relativity was having extremely high influence in his mind. So in special relativity, time is basically a relative time. That is not absolute. Time is not absolute in special relativity. So different places can have different time. So it can dilate and it can contract. So in general relativity also it was maintained that time, even in general relativity, even general relativity doesn't have a concept of universally progressive time. So the universally progressive constant time entity is not there in general relativity. So general relativity, all the different points will have different time. So here is the difference between dynamic general relativity and general relativity. Um, in dynamic general relativity, the spatial changes which are happening are dynamic. That is, they are evolving with time. Now, evolving with what time? So specifically, they are evolving every Planck time of universal time. So there is one time in general DGR which is universal time, so which is basically the same for the entire universe. So it started ticking, this particular time clock, that is the Planck clock, started ticking at the time of creation, and it keeps on ticking every Planck time. Planck time is an extremely small measure of time, 10 to the power minus 43 seconds. But this universal time is there in DGR, but in general relativity, it's not there. So hearing that, most of the physicists will come and point their weapons at me, shooting at me that how dare you say that. But don't worry, even with universal time, there is variable time, rather general relativity pops out of DGR at a certain interval. So just be patient about that. So evolution of spatial changes in dynamic general relativity is dynamic as compared to static. So dynamically evolving spatial changes with Planck time. And general relativity, the spatial changes are static, basically, just like trampoline. Trampoline, there is a basically change in shape of the trampoline. So what he envisioned was change in shape of the fabric of space-time. But this change in shape, what exactly is causing that? He was not. So what are the quantum events that are causing the changes in the shape in the shape of the space-time? He was not really. He did not dig into that. So probably that is the problem. So I'll just go briefly into what DJR is. There are two ways of studying DJR actually. One is to understand what is the present status of the theory. And the second, which is more appropriate way, is basically to understand what is the evolution of the theory. So you start with the present current physics and then go into how the theory started and what were the earlier forms of the theory and how I blundered and where I made mistakes and where the earlier form of the theory was wrong and then how it was changed. So it's a complete evolution of the theory, and then you reach the present status of the theory, and then how the theory can solve all the questions. So this is the right way of understanding DGR, but unfortunately we don't have that much time here. So I think that we'll skip to the present status of the theory at the moment. So there are three theories actually, which are foundational theories of dynamic general relativity. General relativity and quantum foam. That is one prediction of quantum electrodynamics. So quantum electrodynamics is also one of the founding theories of dynamic general relativity, and loop quantum gravity. So loop quantum gravity is also one of the founding theories. So this must have seen foam on coffee. So there are these bubbles which pop into existence and then they burst and they pop out of existence. So popping in, popping out, popping in, popping out of existence. So this kind of a quantum, this kind of a foam is also seen in quantum realm, that is at Planck scales. The description says that they are virtual particles. These are basically minor energy fluctuations. So energy keeps fluctuating up and down, and these virtual particle antiparticle pairs, they pop into existence and then they annihilate each other, and then they reform the energy. So this keeps happening at every nook and corner of the universe. So even at empty space this is happening. So this empty space looks pretty boring actually, but at quantum scales all these events are constantly happening. So virtual particles are popping out of existence, but the problem is that there are two ways in which this quantum foam assumption is different in our theory as compared to quantum electrodynamics. So these virtual particles are actually supposed to not exist. Basically, they are basically I don't know how they came up with this assumption, but they are basically required for mathematics to work. So there are some Casimir effect and all, because which they assume that this is there. But yes, so there is a difference between the quantum foam in quantum electrodynamics and in DGR. In DGR, this quantum foam, so in quantum electrodynamics, this quantum foam, how it works is that it has to necessarily form in pairs. So energy will get converted into a pair. So it cannot form. So this particle antiparticle pairs have to form in pair. So that is the difference between DGR and quantum electrodynamics. Quantum electrodynamics says that they have to form in pair, but DGR says that why should they form in pair? Why not only appearance? Why not disappearance? Why? And there's another slight difference actually. So quantum electrodynamics says that they are just virtual, so they don't have any existence. So they will not add to volume, or they will not take up any volume, or they will not reduce any volume if they pop out of existence. But DGR says, why not? Why not? If they are coming into existence, they must have some volume. They must have some more existence. They must have some volume. So basically, um, so yeah, and LQG assumptions will come to. So loop quantum gravity has some assumptions which we have taken just directly from LQG. That is, um, space time is not flat, not continuous, smooth. It is basically made up of small fundamental units of space time, which are basically, you can say, cubical. They are cubes, or you can say that they are spherical cubes. Imagining cubes is easier. If you have a cube with every side as one Planck length, that the surface area of that cube, of the face of the cube, is one Planck area, and the volume is one Planck volume. So that is the ideal Planck compartment. So this basically the whole space time is basically these cubical regions of space time which are stacked together and bound together. Yeah. So that is what uh, space is made up of. But there are other additional assumptions. I'll come to that. So they are basically fundamental units of space-time, and they are made of Planck length, Planck area, and Planck time, that is 10 to the power minus 43 seconds, is also a very important thing in dynamic general relativity. So basically, everything is basically happening in these Planck scales. So um, so this dynamic general relativity is basically um, in these scales. So Planck compartments are basically like indivisible. So they cannot be divided further. So you can have two Planck compartments, you can have three Planck compartments, but you cannot have 2.5 Planck compartments, or you cannot have two by four Planck compartment, 2 by 3 Planck compartment. Like that, you cannot have a fraction. You can have um, integer number, but you cannot have fractions of number of Planck compartments. So you cannot divide the Planck compartments further into two. But it's extremely small, 10 to the power minus 35 meters. So it's so small that it's practically useless to divide it further. It's so small. It's smaller than electron by multiple times, multiple times. Okay, so these PCs are slightly counterintuitive, because these Planck compartments are basically, they act like marbles. So they are empty space, but they act like marbles, because one Planck compartment cannot take same coordinate location as the another Planck compartment. So here you can see that there is a universal coordinate system. So this is another difference from general relativity. General relativity says that there's no universal coordinate system, so it's all completely relative. One is related to other, and the, so coordinate system can be different for different people. But this is where general relativity and DGR again have come in loggerheads. So there's a universal coordinate system. So one Planck compartment has one coordinate close to Planck length. So one Planck length. So this is coordinate system which is universal, and it is as small as one Planck length. But two Planck compartments cannot take the same coordinate location. So they are like marbles. So they are not exactly empty space. Like a wave, a sine wave, the crests can join up with crests and they add up. But like that, they cannot overlap. Two compartments cannot overlap. So there is another very important assumption, which is called as the PC vacuum. So in between the Planck compartments, what happens is that there's a real nothingness. So this intergalactic space, which is empty, which is having vacuum, is actually not vacuum, because it's made up of these Planck compartments. But these blank compartments also have a small area which is called as PC vacuum. So, but it's actually not allowed. So if anywhere PC vacuum happens, then all the surrounding blank compartments are pushed or pulled towards each other, so that you have to compensate, or you have to negate the PC vacuum. So PC vacuum should not exist. So that is one of the assumptions of DCR. Now, these virtual particles which are appearing and disappearing in quantum form are actually particle and antiparticle pairs, I said, are basically appearing and disappearing Planck compartments. So these Planck compartments can appear and disappear, appear and disappear. So they pop into existence and out of existence. And so the particle version is the destruction of a PC, popping in out of existence, and the antiparticle version is the popping into existence. So popping out in out like that. So these PCs, the whole universe, basically everywhere, every corner of the universe, these Planck compartments are popping in and out of existence. So this is basically directly taken from this quantum form assumption. So the whole universe, you can say, is made up of two components: manifest component and an unmanifest component. So you can just see, imagine that there are three PCs. So they are in the same line, and the central PC just disappears, pops out of existence. So what happens is that here a Planck volume, one Planck volume of Planck vacuum is created. So this vacuum causes all the Planck compartments around to be pulled towards each other. So these two PCs are going to be pulled towards each other, and so this Planck vacuum which is there, that can be called as zero. Okay, and then this manifest component of the Planck compartments can be called as one. So you can see that the whole universe is basically made of these ones and zeros and ones and zeros and ones and zeros. And every Planck time, the whole universe is rewritten. So one Planck time, this universe, then again the second Planck time. So this is a very, very weird direction in which DGR is hinting. So these Planck compartments are basically popping in and out of existence every Planck time. So it can be faster than Planck time also, but at these Planck scales basically of time. So there are some things which you just cannot deny to be true. Even Einstein cannot deny it, or no physicist can deny it. That Newtonian apple falls down, or for that matter anything, even a meteorite or a ball which is thrown up, it will fall down basically. Why it falls down, we don't, but it falls down. So it falls down, and galaxies move apart, so the universe expands. So we can say this, that the space just below the Newtonian apple is actively contracting. So there's an active contraction of space, and the space in between galaxies is actively expanding. So this can be considered as an assumption of this theory, or whatever. Now, this is an observation which you just cannot deny. So active contraction of space is possible. This is an assumption. Okay, so active contraction of space is basically additional destruction of pieces. There is this quantum form, and there pieces are being created and destroyed, but there is additional destruction. So there's more destruction, unbalanced destruction. So there is creation, but there's more destruction than creation. Then what happens is the total number of space collapses or contracts. And also, if there's an active additional creation of new pieces, then the total amount of volume will increase. So the active expansion of space can also happen. So these are additional assumptions, that is, if space is there, it can actively expand or it can actively contract, depending on what processes is predominant there. So if destruction is predominant, then it will actively contract. If creation is predominant, then it will actively expand. And if there is balance creation and destruction, then the space will remain the same. So the volume will remain the same. So it will not expand or contract. So this is where DGR is heading to. Every nook and corner of this universe is being created and destroyed and recreated, and continuously the cycle keeps going on. Creation, destruction keeps happening relentlessly. So now we'll come to gravity basically. So the general relativity described by Einstein says that the Earth, what it does is, because of its mass, all the constituent particles of the Earth, they cause a time dilation wave. So if you imagine the Earth, you can draw spherical time zones around the Earth, and this closest to the Earth, closest to the surface. These time zones, basically, the closest to the surface will have maximum gravitational time dilation. So this is the prediction of general relativity. I'm not saying about DGR. So general relativity says that the innermost time zone will have maximum gravitational time dilation, and the time will this gravitational time dilation will keep reducing as we go up. So imagine that this one particle P is there, and it is under active influence of Earth's gravitation. So at any given point, P's location is there, at a height h, and we can basically draw. You can draw a skyscraper from the point M towards point P, and with this skyscraper can be with cubical compartments, which of your choice. Basically, you can have that 1 meter cube, or you can have them 1 centimeter cube, or 1 millimeter cube, or you can have them 1 Planck compartment as well. So whatever happens, the even if you draw a skyscraper with Planck compartments starting from M to P, the total number of Planck compartments is going to be an integer number, and it is basically going to be a finite number of Planck compartments. That we know for sure. Now, as P comes down, what happens is that this Planck compartment skyscraper will keep on reducing in size, which means that the total number of Planck compartments is reducing in this particular particular skyscraper. But there won't be any 1.5 or 2.5 or 3.5 Planck compartments. So it's basically going to be an integer number. But that's not the case with other volumes. That is, if you are thinking of another volume that is 1 meter cube, let's say think that it's not Planck compartment skyscraper, it's a 1 meter cube space skyscraper. So we can number these actually. So the lowest one we can number 1 and 2 and 3 and 4 and so on. So the first or the lowest 1 meter cube cubical compartment will have the maximum gravitational time dilation, and as we go up the skyscraper, the amount of gravitational time dilation will keep increasing as keep decreasing as we go away from so the closest one will have the maximum gravitational time dilation. So what if we think that this quantum foam is directly linked to the extent of gravitational time dilation? So if gravitational time dilation causes this quantum foam to deviate towards destruction, that's what I had thought before, and that is how I came up with what if there is a link between this, and that is how the whole thought process started. What if that gravitational time dilation causes the quantum foam to destroy more Planck compartments as compared to. So basically, you can think that P and Earth are at the same point but same location basically. But the number of Planck compartments in this skyscraper is basically being destroyed. So there is active loss of volume in each of these 1 meter cube compartments. So these all these each and every of these 1 meter cube compartments is going to actively contract, and they are going to keep losing. Now I'll just explain to you what exactly it is. If it is very difficult to understand, I will continue the tradition of using an apple to explain. Imagine that apples are equivalent to pieces, and imagine that you are a fruit vendor and I am a supplier, and you have 100 apples. So in the first cycle, basically I give you 20 apples, and I take back 15 apples. And the second cycle also the same thing happens. I give you 20 apples and I take back 15 apples. Third cycle again 20 apples. I give and I take back 15 apples. Like that, cycle 4, cycle 5, cycle 6. So every time you are basically gaining 5 apples. So if you had 100 apples before, you will then have 150, 100, so whatever. 105, 1010, 115, all that. Now think about it. These cycles are happening at Planck scales. So at 1 second, these cycles will happen 10 to the power 43 times. So in 1 second, 10 to the power 43 cycles like this will happen. So your basically the heap in front of you of apples is going to keep increasing tremendously. So you are going to keep gaining a lot of volume. Now this works the other way around also. If I give you 20 apples, if I take back 25 apples, so at every cycle, basically what is happening is that you are losing 5 apples. So you had 100 apples, but now you are having 95, then 90, then 85. So the total number of apples with you will keep on reducing. So the heap in front of you will keep on reducing. So that is very simple actually. But remember that these are not apples, these are pieces. And remember that this is basically one point in space. So you are a fruit vendor for one point in space. There are millions, billions, trillions, quadrillions, quintillions of such points, and so there are quintillions of such fruit vendors, and this cycles are happening in which so nearer the Earth, what is happening is that these cycles are happening in which this destruction is more than creation. So there is an active spatial contraction. So this outward cube is basically contracting, so it's losing volume, and so the neighboring cubes have to take. So it cannot form a void outside it. So the neighboring Planck compartments have to react to it, and it has to compensate for this active spatial contraction by having some changes in them itself. So these are basically assumptions related to space for DGR. So there are some time related assumptions also. So space related assumptions, they are made up of Planck compartments, and small and time related assumptions are these. I've already spoken to them about that. But there is basically universal time. So there's one time which is absolute time, and it keeps ticking every Planck time, and this is universal time. It's universal everywhere. And the second is the local time. So this local time is a illusionary time. So it is the only time which we can measure. So we cannot measure this universal time. I will explain to you the local time much more in detail later. But this is an illusionary time. So it's not a real time. It's not, but it's extremely important because all our instruments of measuring devices, including the atomic clock and the photon clock. Photon clock is the most accurate one. So all of them, it's an imaginary clock, isn't it? So even photon clock cannot measure the universal time. It has to measure only the local time. You cannot measure the universal time. You can decipher it, but you cannot measure it. So the only thing which we can measure is local time. So anyhow, so there are three process related assumptions. So there is creation happening, there's destruction happening, and there is entanglement happening. So this entanglement is basically the thing which we are supposed to understand. This creation and destruction, let's say assume that there's one point in space, and there destruction is active destruction is happening. So 100 Planck compartments are being destroyed every Planck time. So what happens is that at the end of this Planck time, what happens is that there's a void created of 100 Planck compartments around, just for explanation sake. So this void is not allowed actually. So the surrounding pieces immediately get entangled and they are pulled inside. So they're pulled inside. So just around this particular, you can imagine concentric spheres all around it. So you can number these spheres: the first sphere, second sphere, third sphere. So this is one PC thick spheres. So the first sphere will basically get entangled. So they'll be pulled inside. The first sphere will be pulled inside. They will lose volume and it will be pulled inside. So the PC volume will be shifted out of it. So it will be shifted immediately inside the second PC sphere. So the second PC sphere gets entangled. So all these PCs then again start reacting. So this is a reactionary. So these pieces, what they are doing is that they are trying to compensate the void. So this is basically compensation. So creation, destruction, and compensation. So these are the three things which are happening here. Okay, so even if creation is happening, excessive creation, so they will push the pieces apart. So if multiple pieces are being created, so the pieces will get pushed apart. So there is something called a C by D ratio. So this is absolutely relevant in our case. So creation and destruction ratio is called as C by D ratio. So if the C by D ratio at any point in space is basically deviated towards destruction, then there is more destruction than creation. So there is active loss of volume. But if it is more creation than destruction, then there is active gain of volume. This is basically very simple. So you can understand that you can see that there is a small void over here. So these marbles or these Planck compartments, uh, just immediately around it will be entangled. So these entangled pieces will start being pulled inside inward. So it's basically eating up those pieces. So once it is pulled inwards, it cannot go inwards unless it has some volume loss. So they'll lose some pieces and it will go inside. So basically it's like a dominoes, like one domino falls and it forms a wave, a reactionary wave, and all the um, dominoes start falling. So one after the other, one after the other. One fall of domino leads to the other fall of dominoes, and second, and then the third, then the fourth. Like that here, you can imagine concentric spheres all around. So the first level sphere will react, then the second layer sphere will react, the third will react, and the fourth will react. So these spheres will basically react to PC vacuum being formed, and they will be pulled inside, and they will form. They will have volume contraction within them. So it's like so the central domino starts falling, and the reactionary wave starts going like that. So it's like dominoes. Okay. So here again that the first layer has basically disappeared and it has gone inside. So the second layer now becomes entangled. So the second layer is being pulled inside because of the PC vacuum. So now the third layer gets entangled. The second layer forms this layer, and now here you can see another event of destruction has happened. So even this part will get pulled inside. So now these PCs will react and they will go inside, but they will develop a vacuum volume change, volume loss, and then the outer part, outer that is the fourth level of the PCs will start getting entangled. So this reactionary change keeps happening. You can see if I just make it fast. Now these things are basically happening at an extremely rapid rate of the reaction time of the pieces could be anything actually. It could be every Planck time, or it could be if the number of events that are happening there is much more. That is, if there are 100 pieces being destroyed in every Planck time, then this reaction time of these pieces are actually not. These are basically fundamental units of space time. So it's just space time. So it's not violating general relativity. General relativity doesn't put any restriction on how fast the space can expand and time can reset. So this is basically the time is getting reset in this. So these are basically circular or spherical, and these are aggregates of pieces. So that's the reason why you can call them as eddy Planck compartment aggregates. The eddy means what? It's a circular thing which forms at a point of low pressure. So eddies are formed around a low pressure area. So these are eddy like, and these are Planck compartment aggregates. So they can be called as EPCAs or eddy Planck compartment aggregates. So if there is a excessive destruction happening, or if there is an excessive creation happening anywhere, then eddy Planck compartment aggregates are formed all around it. So they are reactionary. So they are basically meant to compensate for the void. So you can say that they are meant for compensation of the void, or meant for basically the push which is done because of the excessive creation. So any excessive deviation of C by D ratio at any point, if C by D ratio is deviated towards destruction or creation around them, compensation happens by formation of these eddy Planck compartment aggregates. So these eddy Planck compartment aggregates are basically of two types: circular EPCs and linear EPCs. I will come to the linear one. But here we have shown some small. Can you see that here is a PEP, that is a positive energy particle. That is, there is a positive energy happening here. That is, there is an excessive amount of destruction happening with it. So as soon as the void forms, the first level PCs are going inside. So the second level PCs will start interacting. Now here, what is happening is this second level PC. This is basically a diagrammatic image. Don't take it too literally, because I've drawn them. So basically, the Planck compartments are looking of different sizes, and there are basically lots of gaps inside, which is not the right thing actually. But anyhow, so this you can say that this is the third level. So the second level is almost going inside. Only one PC of the second level is shown, which is also not right. But you can imagine that the second level goes inside, and the third level, just immediately inside third level, Planck vacuum is created. So these third level PCs will have to go inside. They will be pulled inside. But once they are pulled inside, what happens is they have to basically all of them will be destroyed and then again recreated. But while recreation happens, the sphere reduces in surface area. So there's not enough surface area left for all the recreation. So additional destruction happens. So basically there's active volume contraction. So these curved EPCs are having curvature. So that when the PC vacuum, what is happening here is that PC vacuum is being shifted from here. The PC vacuum is shifted to here, then PC vacuum is shifted to here, then PC vacuum is shifted to here. So what is happening here is that so the total number of so the surface area on which the same PC vacuum will be shifting will keep on reducing as the PC vacuum is shifted outwards, and the same PC vacuum shifted to more and more surface area means that basically the inner PCs EPCs will have to move much more distance, and the outer EPCs will have to move much less to compensate for the same void. Now, this is a bit difficult to understand at first, and I think that you will need to read the book to understand it. So these are called as linear EPCs. So now, this EPCA, these EPCAs, or these are you can call time resetting waves, basically reactionary waves. These reactionary waves keep traveling outwards from the central part of the positive energy particle. So they keep traveling outwards. So as they travel, they can there's no stopping them. So they can travel for 1 meter or 2 meters or 100 meters or 1 kilometer or 1 light year. They'll just keep traveling. So at extremely large distances, what happens is that the PC vacuum is just the PC vacuum is shifted, and there's no curvature. So if there's no curvature, it's just that it's just this PC vacuum gets shifted. This EPC shifts down, and PC vacuum shifts up. So then again, so like that, these are the linear EPCs. So basically, DJR suggests what that every constituent particle of the sun has extreme amount of energy within it, and energy is basically destruction. Positive energy is destruction. So the sun, immediately around the sun, the PCs are getting eaten up. So what happens is that EPCAs are formed all around the sun. So closer to the sun, the EPCAs are circular or spherical EPCAs, but very, very far away from the sun, the same EPCAs will become will no longer remain spherical, but they'll become linear EPCs. So these linear EPCs are absolutely relevant for explaining MOND. So now, what is MOND? MOND is basically modified Newtonian dynamics. So linear EPCAs are basically utilized in dynamic general relativity to explain why gravity behaves differently at extremely large distances. Basically, because the EPCAs are no longer curved EPCs at that realm, and they become linear EPCs. So linear EPCs will mean that the acceleration due to gravity no longer reduces, but actually becomes constant. So acceleration due to gravity just becomes constant. Now, I won't be able to explain to you in too much detail about this. You will have to read the book for that. Anyhow, now we'll come to this local time. I'll just give a small explanation about what local time is. Imagine that there is a pendulum, and the ball of the pendulum you can imagine to be some ferromagnetic material like metal, that's iron, and it keeps swinging left to right. So you can measure time. No, I will not go into detail of how you measure time, but you can calibrate the pendulum, and because the mass of the pendulum and the Earth's gravitation will remain the same, so it will swing at the same rate. So if in 1 minute X number of movements it does, cycles it does, then the next time when you see that yes, it is moving that much amount of 20 or maybe X number of cycles have come, so you can be sure that you can measure time that way with the help of the pendulum. So if what happens if we rig the pendulum? Imagine that you have kept 2 electromagnets, and when the pendulum is swinging, when it comes to the point L, the left magnet starts, and it momentarily pulls the magnet towards itself, the pendulum towards itself. Then again, L starts going towards C, and then it reaches R. So as soon as it reaches R, the second, the right magnet momentarily pulls it. So in this rigged kind of a setup, what happens is that the swing of the pendulum will actually be reduced basically. So if some scientist is given this rigged setup, and scientist doesn't know that this is a rigged setup, so what will he find out is that this pendulum is showing delayed time. That is, the time is it's not swinging properly. It's showing delayed time or dilated time. So the similar thing can, similar setup you can use for a photon clock. So this is a photon clock, the left side mirror and the right side mirror, and a photon which is bouncing up and down. And just for the imagination's sake, let's think that the distance between left and right is basically 100 Planck lengths, so that this photon, it will basically move one Planck length in one Planck time. So in 100 Planck times, it will go from left to right. So it will basically measure 100 Planck times minimum. Now think about it. What happens if there's an actively expanding space just behind the Planck, the photon? What will happen is this actively expanding space will push the photon faster, so that it will reach R much earlier than. So basically, special relativity says that photon has to travel one Planck length in one Planck time. That's it. Whatever happens. But this active spatial expansion just behind it, even if it is moving in front by one Planck length in one Planck time, there's active spatial expansion behind, which is basically pushing it forward. So even if it is moving at one Planck length per Planck time, it will reach earlier. So this basically what is happening is, if there's an active spatial expansion, the photon clock will start ticking faster. So it speeds up. This speeds up the rate of ticking of the photon clock. So active spatial expansion causes time to contract. Actively expanding space behind the photon in the photon clock causes the photon clock to tick faster. So wherever space is actively expanding, there is a time contraction. So here we come to one of the predictions. That is, if you send a atomic clock, which is or photon clock, if we have the, and we send it in the intergalactic space where the galaxies are expanding. So there, what will happen is that there is active spatial expansion. So the time is actually contracted over there. So the clock will start ticking faster, much faster than it is here. So if you are comparing these two, this is a practically useless method, because you cannot really send a spacecraft in the intergalactic region. But it's actually theoretically, yes, you can check the difference, and there will be a difference that intergalactic region where the space is actually expanding, there will be something exactly opposite to gravitational time dilation. So here there will be a time contraction. There will be contracted time. So again, if the space just behind the clock, the photon, it's not expanding actively, but it's contracting actively. So it's losing volume. Then what happens is that the photon, basically the forward journey of the photon will be prevented from happening. So it will slow down the photon. So you can see that dynamic general relativity is basically hinting towards what? It is hinting towards a variable speed of light theory, which was actually given by Einstein in 1911. Unfortunately, the physicists did not give much attention to it, and that is probably the reason why physics has not progressed since 1 century. So it's the progress of physics has halted because people did not give much attention to the VSL paper of Einstein, 1911 paper, in which he had suggested all these things, that This in that paper he had suggested that if the speed of light is constant and um, in a curved space time, whatever predictions of general relativity are we are seeing, the same predictions can actually come with variable speed of light and flat space time. So here we are saying that the space time is flat, but there's active spatial contraction or expansion that causes the photon, the velocity of the photon, to increase or reduce. And so it's a variable speed of light here. So speed of light is actually varying over here because of active spatial contraction or expansion. So here again, actively contracting space behind the photon causes the photon clock to tick slower. So this is basically applicable to any clock. It's not only applicable to a photon clock, even a atomic clock. If you consider an atomic clock, cesium clock, and the cesium is vibrating, and just behind the cesium clock, because these are events which are happening in Planck scale, so that's much less sensitive than as compared to I mean the photon clock, the atomic clock is much less sensitive than this. So these events are happening much faster than we can fathom. So um, so even the atomic clock will be slowed down if there is an active spatial contraction. So here, nearer to the surface of the Earth, dynamic general relativity says that the gravitational time dilation which we are seeing is basically because of active spatial contraction which is happening over here, which is basically happening because of active destruction which is happening in each and every constituent particle of the Earth, which gives mass to the Earth. So mass of the Earth causes destruction at each and every core, which causes EPCA formation, which is basically basically leads to active spatial contraction. And this active spatial contraction is causing the time dilation. So this time is actually an illusion. It's not a real time. So whatever special relativity and general relativity are saying about variable time is right, but it is just an illusion. It's not the real time. The real time, there is a time is absolute. Okay, so dynamic general relativity, what does it say about energy? Any deviation of the C by D ratio towards creation or destruction is energy. Okay, so if you deviate the C by D ratio towards destruction, that is, if there is an active loss of volume, there is active spatial contraction. Why we are saying every time active, because it keeps evolving every Planck time. So every Planck time, this many number of pieces are getting lost. So every Planck time it is evolving. It's a dynamic process. So it is evolving every Planck time. So wherever there is active spatial contraction or wherever there is time dilation, there is positive energy. Contrary to that, wherever there is active spatial expansion or there is gain in volume, or if wherever the C by D ratio is deviated towards creation, at that place negative energy is said to be there. So it's very simple. So positive energy is destruction and negative energy is creation. So now we come to very important concepts in dynamic general relativity. There's something called as a T is equal to zero compartment. That is, it's a compartment or a point or a place in which there is a tendency of C by D ratio deviated towards 1 by, that is C by D ratio here is 1 by 2, that is 0 by 1. Now, 0 by 1 is a bit of a non-intuitive ratio, but basically what we are saying is that here one Planck compartment is being created and two Planck compartments are being destroyed in one Planck time. So every Planck time, one PC is getting created and two PCs are getting destroyed. So what's happening is, or maybe zero PCs are being created and only one PC is being destroyed. So we are basically essentially a volume equal to one Planck compartment. That is, one Planck volume is getting destroyed. Now, why are we calling this as a T is equal to zero? Because time, local time, Universal time keeps ticking the same pace, but local time over here has become zero. So why we are saying like that? So if you imagine that there is a Planck compartment over there, and then there's a photon which is basically stuck in there, and it tries to move out. So in one Planck time, it will move one Planck length, but then this again will destroy one Planck length. So every time one Planck length is getting destroyed, and this basic basically this photon which is being trapped inside this t is equal to zero compartment, it cannot just come out. So the if you are putting a very miniature Planck clock inside this Planck clock, this Planck this just keeps just cannot move out of that compartment. So the photon will stop ticking. So the Planck clock will stop ticking, which means that it is a zero. Time is equal to zero. So time has turned off. But that is only local time. Local time is turned off. The universal time keeps ticking over there as well. So t is equal to zero compartment is basically a fundamental unit of energy in DGR. So what happens if two t is equal to zero compartments come together? Well, as we said earlier, that just outside it, the compartments keep getting sucked inside. So it'll keep sucking, and it'll keep creating what are called as time resetting waves, and it'll form EPCAs. So EPCA forming time resetting waves will start forming around it, and these will interact, and time resetting waves of two t is equal to zero compartments can interact, and they can basically add up. So basically two t is equal to zeros can attract each other, and they can basically form aggregates. So uh, 2t is equal to zero compartments can aggregate, 3 can aggregate, 4 can aggregate, 10 can aggregate, 100 can aggregate, 10 to the power 10 can aggregate, 10 to the power 1000, 10,000. There is no upper limit to it. So many number of t is equal to zero compartments can aggregate together. And so what does that mean actually? So if there is just 10 or just 100 or just 20,000, so there's much less energy. But if it is 10 to the power 10, 10 to the power 10 to the power 10,000, then it's much more energy which is being packed in one particular small area. So if they are very small, then they will form uh, basically photons of basically photons of positive energy photons of maybe infrared initially. Now if you increase the energy further, then it will be visible light, then further increasing the energy, and it will become ultraviolet light, and gamma radiation. So if you increase the energy so much that it collapses, so it what happens is that it forms a particle with mass. Even further, much more, uh, many t is equal to zero compartments are getting clumped together. What it forms is a black hole, and then the central supramassive black hole, and then it keeps on going. So there is no upper limit to how many t is equal to zero compartments can combine together. The more t is equal to zeros are combining together, the more is the mass, and the more is the destruction happening at that point, and the more reactionary changes will happen over there. So this t is equal to zero compartment is fundamental unit of energy. So there is one God equation. You can say that people are looking for that equation. So probably DJR is hinting towards this God equation. There is a some equation which is equating the loss of volume to energy. So whatever energy units we have, they should have some connection with destruction of volume. So how many PCs are destroyed in one blank time? That um, that equation we still don't have. We need computer models for DGR, and only after that we can calculate that equation. But that equation, here we are just hinting towards that equation. So these are, so what if t is equal to zero compartment is there, what is the um, other counterpart of that. So it's called as the T is equal to T max compartment. The nomenclatures are not very important, and they are given by me, but they can be changed later if needed. But here the C/D ratio is deviated towards creation rather than destruction. So basically, what is happening here is two Planck compartments are being created and one is being destroyed. That is essentially 1/0. That is, one is being created and none is being destroyed. So essentially, we are gaining one Planck volume. Now, this is also very, very important, because imagine that there's a small place where C/D ratio is 2/1. What will happen is that every cycle, um, one Planck volume is extra Planck volume from nowhere is being created. So if you have one PC and two PCs like that, you form a chain of these PCs, and in 1 second, this particular point with a C/D ratio of 2:1 will form 10 to the power 43 Planck volumes, which is actually something which is 1 meter long, which is a significant amount of volume for a quantum particle. It's such a small particle. It's a very huge amount of volume which is being created at every second. Every Planck time, one Planck volume. So 10 to the power 43 Planck volumes are being created every second, which is an extremely high amount of volume. So this is a T is equal to T max compartment. So it is the fundamental unit of negative energy. So what will it's also called as ENEA particle, or exotic negative energy antiparticle. It's called. So this is the antiparticle version in dynamic general relativity, DGR. So this is an antiparticle. Anyhow, so what will happen if these two interact with each other? So immediately outside, what happens is that whatever pieces are there outside this particular T is equal to T max compartment, they will what they will do is that they will be pushed outwards with so much creation happening. They'll be pushed outwards. So they will form negative energy PCs. Now I'll have to go into detail of that. I don't want to waste time about that. But basically, the surrounding PCs also will form eddy Planck compartment aggregates, and these Planck compartment aggregates will have additional creation. So they will also have active spatial expansion. So basically, at this point, all around the this particular point, there will be active creation happening, and there is active spatial expansion happening. So if there are two T is equal to 0 T is equal to T max compartments coming close to each other, they will basically repel each other. They will not form aggregates. They cannot form aggregates. Okay, so they will just remain away. They will not form together. They will not interact. So they are basically negative mass particles. So they have a negative mass, and so they are an excellent candidate for dark matter and dark energy. So we don't know yet, but what teacher is hinting is that dark energy and dark matter both are basically made up of ENEA particles. Now this is one of the predictions of DGR. We don't know yet. Now we'll just go to time resetting waves. Okay, so any place where there is positive energy excess, that is a C/D ratio, the creation or destruction ratio is deviated towards destruction. So there's excessive amount of destruction happening at one point. So what is going to happen is that you will have to draw one Planck compartment thick circles or spheres all around this point, and you have to keep naming them. So 1, 2, 3, 4, 5, 6. So first level, second level PCs, third level PCs, fourth level PCs, like that. So all these PCs will start reacting to the destruction or the PC vacuum formation in the center, and they will basically go inside. So they will be pulled inside. So whatever PC vacuum is there, that will keep moving outwards. So this is like dominoes. So what will happen is that each of these EPCAs will have an active spatial contraction. So essentially what is happening is that active spatial contraction and time dilation is happening. So immediately after around the positive energy particle, what is happening is time is getting reset, and this time resetting wave, which is EPCA forming time resetting wave. So EPCA forming time resetting wave moves outward. But how fast will this time resetting wave move? Now, if general relativity has to be believed, it will, nothing can go faster than the speed of light. So it should go with speed of light, but which is not true. The reaction time of these pieces can be one by hundredth of a Planck time, or 1/1000th of a Planck time, or one by 10 to the power 10 to the power 10,000th of a Planck time. So that can be anything. Okay, so there's no lower limit. So here again, DGR is basically deviating from loop quantum gravity. Loop quantum gravity says that one Planck time, that's it. There's no time smaller than that. But DGR doesn't say like that. So there is no lower limit to the reaction time. So that's why these time resetting waves can travel pretty fast, very, very fast, much faster than speed of light, much faster than speed of light. How fast, we'll have to make models, and we have to see, we have to check, and that will take time. We'll have to check, make models of DGR, then we have to see what they predict, and whether they predict whether Newtonian gravity, it should pop out. I think it should pop out. Newtonian gravity pops out, and general relativity pops out. But we have to ensure that the model um, is right. So anyhow, if there is a positive energy particle at one particular place, then you have to realize that the spatial changes which are happening around it are the primary event, and the time which is getting reset because the active spatial contraction is happening is basically secondary. Okay, it's basically the time resetting is the local time. It's not universal time. Universal time will go in the same pace, and the local time will get reset, and the local time will start developing because if there's active spatial contraction, it will cause time dilation. So this time dilation wave will keep moving outwards at extremely fast rates. We don't know for sure how fast it will go, but I think faster is, the more the number of events per Planck time, the faster the movement will go, which essentially indicates that gravitational interactions are extremely fast. They are not moving at speeds of light, and so gravitational interaction of the sun has much less mass, so its interactions will go slower, and the gravitational interaction of a much bigger massive star will be much faster than the gravitational interaction of the sun. These are some hints which DGR is giving towards, which might turn out. So that's how theory should be giving some predictions which are testable. So if it turns out to be wrong, then this is a falsifiable. So the DGR is a falsifiable theory. So you can falsify it. Okay, you can prove it to be false. Okay. Anyhow, so imagine a sphere, and there are 100 Planck compartments at the surface of the sphere. Imagine that this sphere is basically around a Planck positive energy particle at the center. Okay, so this is basically, let's say it's the third um, level sphere. So what will happen is that there is a PC vacuum formed at the center. So the first, second level will go inside, and then there will be PC vacuum formed inside. So if PC vacuum is forming inside due to destruction, what happens is that these pieces will get pulled inside. So the surface area of the sphere reduces. Once the surface area of the sphere reduces, active spatial contraction is happening. So we saw in the Planck clock there that active spatial contraction wherever happens, there is a time dilation. So here in this EPC, there will be basically active spatial contraction, and that's why time dilation will happen. So the PC vacuum will shift outward, and so the pieces immediately outside will now get entangled. So these are basically time resetting waves. Okay. So gravity is basically explained because of these time resetting waves. So active spatial contraction and time dilation. So here we will just end actually, because so I'll just give a brief summary of what are the elegant features of DGR. DGR basically can explain gravity very nicely with EPCs. It's a quantum events that are happening, which ultimately lead to gravity. It can explain very nicely. This is a very brief introduction actually. So some of you might not have understood it, so you will have to read the book for properly understanding it. But anyhow, the gravity can be very nicely explained with the help of DGR. And the gravity, it's basically able to explain all the predictions of general relativity, including gravitational lensing and gravitational time dilation, as well as gravitational redshift. So gravity, as far as Newtonian or Einsteinian gravity, it can very nicely explain. It can also nicely explain MOND, although we don't have exact equations and mathematics of it. So we have to be a bit skeptical whether it is same as MOND. But I think that the linear EPCAs will very nicely explain why MOND is happening. So this is a very important thing, that we don't really need dark matter here, and MOND will be able to explain everything, and DGR hints towards MOND to be reality, modified Newtonian dynamics rather than dark matter. So it doesn't really need dark matter for that. And so it is very nicely making quantum mechanics and general relativity compatible. Now, how it is doing that, you'll have to read the book for that. But this is my claim basically. You will have to analyze it, and you'll have to come to a conclusion which is whether it's true or not. But I really believe that it's very nicely, elegantly, it converts quantum mechanics into, variable background theory in quantum mechanics. So the force carrying particles are turned into time space-time changes in dynamic general relativity, and also the time of quantum mechanics and general relativity. The time problem is also solved very nicely with DGR. It can very easily explain wave particle duality of matter as well as light, because it is basically ingrained in it very nicely. So here the particle, it's a realistic theory actually. It believes in realism. So the electron is real, and it has its own particular existence to a very precise one Planck length coordinate location, but its movement is very fast also. So the electron can move. The electron can move much. I mean, at Planck scales it can move. So maybe in every 5 Planck scales, Planck times, the movement, the position of the electron might change. So these are unfathomable to us. So that is the reason why that is how it explains the uh, the quantum mechanics, how it is not, it's a probabilistic theory. Why it is probabilistic? Because the things which are happening are extremely fast, so they are happening at Planck times, so they are unfathomable to us. So we will obviously get a probabilistic type of mathematics here. So it can explain satisfactorily what is in the this basically electrons will have a proper location, and the wave which is associated with the electron is basically reactionary wave, the surrounding pieces which are reacting to the presence of electron. It can very nicely explain inertia, momentum, kinetic energy. It can explain what is there in black hole, singularity, and information paradox. So I think that it is a most awaited theory in fundamental physics since a century, and I really believe that it tells us something about the reality. So it's a no-brainer that most of the physicists should have a look at it, and you have to keep the physics hat outside before you read the theory, because you have to the most important problem I believe is that there are preconceived notions or prejudices which we physicists have. So you have to keep them aside. So you have to keep thinking out of the box. Unless you do that, you won't be able to understand dynamic general relativity. But it is something very, very interesting, and I believe that all physicists should have a look at it. So there are other, so multiple potentially testable predictions are there. There's successful reconciliation of quantum mechanics and general relativity. It's a bridge theory between LQG and string theory, and it solves dark matter and cosmological crisis. It's a potential theory of everything. So there are some pitfalls actually, like it's still in infancy, and math is there are two types of math actually. Some math is relatively easy, and I could not derive it completely because I'm not with math background basically. So whatever is there in the book is basically undergraduate and graduate level math. I have no expertise in differential equations and calculus and all, but actually calculus is not needed for that. It's a different kind of math which is needed for that. The problem with math, deriving math of dynamic general relativity is slightly different. You need to do only addition, but you need to do that 10 to the power 10,000 times, 10 to the power 20,000 times. So the lengths which are involved are not normal lengths, they are sub-Planck lengths and sub-Planck time intervals. Time intervals are extremely small time intervals. So whatever is going to happen, you have to keep repeating the very small. So basically, you need supercomputers to do the math. You need to do just addition. It's summation. There's no integration here because you cannot further divide. So there's no use of calculus. You cannot use calculus here because everything is so small already. You cannot further divide it into smaller intervals. So you can derive smaller time intervals. But the math basically, I think it's a different kind of a math. So you don't need differential equations and calculus and Hamiltonian. And yes, all these things will be needed definitely. What I believe is at the end of the dynamic general relativity, we saw higher dimensions and string theory. So it's a bridge theory. So that is why the mathematics of string theory as well as quantum gravity are going to be tremendously useful to derive mathematics in DGR. So there are some pitfalls basically. It's not hunky-dory, everything is not good. But I think that all physicists should have a look at it. And I think you should get ready for a completely new paradigm shift in understanding physics. So in physics, in the sense in quantum mechanics and general relativity, both it will completely transform the physics of the future. So if you any of you want to contact me, you can email this if you have any doubts, or if you want some collaboration or something. You can contact me on this email, and also you can follow me on Twitter, or you can DM me. You can send direct message on Twitter. And this book will be available in this website, www.notionpress.com within India, and outside India also it will be available on Amazon and Kindle. And also, so if anybody wants to have, you can send me an email and I can send you a PDF copy also of that if you wish. Um, but I want all the physicists to have a look at this particular DGR and analyze it properly, and before throwing it, pushing it under the carpet, because I think it is definitely worth. It's just a 600 pages book, so and without any mathematics, so most of the physicists will be able to grasp what is given in the book. So there are some other books which I have written. This is How the Homo sapiens Blundered. It is a book on climate change, and this is a book which I call Decoding Human Psyche. It's on psychology, how the human psyche works. And this is basically the first book led me to the second book, and the second book led me to the third book, because I understood the psychological concepts of prejudices, and how the human mind works, how it gets trapped. According to me, the physics community has the mind of a physicist, a PhD holding physicist, or higher physicist. It is basically trapped in a rabbit hole of one particular direction of thinking. So you have to change that direction of thinking. You have to come out of that rabbit hole of prejudices. Unless you come out of them, you won't be able to understand DGR. So as I said, you are wearing a physicist's hat. You have to remove that hat and you have to keep it aside. You have to understand that what we all the preconceived notions of prejudices need not be true. So thank you very much for watching, and I hope that you will like it.